So today I'd like to share with you a CPU I designed in a piece of software called Logisim. Logisim is just a circuit simulation software. It allows you to uh, insert gates like this and then create circuits going from there. It's really useful if you're starting out trying to learn circuitry, and it's free, so I'll include a link in the description to a place you can download it. But anyway, for this project, the aim was to create a CPU from mostly elementary gates, meaning like gates like AND or NOT. Logisim offers lots of complex components such as an adder, but instead of using these, I was meant to create an adder out of the elementary gates themselves. So before we get into it, I'd just like to say that most of the information about this I learned was from a book called Principles of Computer Hardware by Alan Clements, and it tells you the basics and has some of the circuits were taken from there, or designs of the circuits were taken from there. So I suggest you check that out if you want to learn more about that sort of thing. Let's get into it. So the CPU itself has, well, it's a 1.5 address machine, which means that it's basically a 2 address machine, but one of the operands is always a register. It has a single bus to transfer data between components. It has 32 addresses of 16-bit memory. It has 4 data registers that can be used in calculations. Those are all 8-bit. It has a program counter, a memory address register, an instruction register, a control unit which controls everything in the circuit, sets the tri-state gates, and an ALU which is capable of addition, multiplication, subtraction, all of the logical operations that AND or NOT, XOR. That was the brief that I was given. So Logisim allows you to make sub-circuits, which is very useful. It means that circuits don't get clustered, saves space, and just makes it easier to look at. So, for example, a sub-circuit sits at the program counter. Sub-circuit looks like this, and then that itself contains a sub-circuit, which is an incrementer. The CPU uses the fetch-execute cycle. By that, it means during the fetch phase, instructions are fetched from memory and then input into the control unit. Once this has happened, the execute phase is started, where the control unit itself decodes the instruction that's been given to it during the fetch phase and sets the appropriate tri-state signals at the correct time to move data around the CPU in order to execute the instruction. Once the instruction has been executed, the control unit resets into the fetch phase, ready to get the next instruction from memory. So now we'll look at some of the sub-circuits inside the CPU, and then after that we'll have a look at how they all work together to fetch and execute instructions. So firstly, the program counter. The program counter stores the memory address of the next instruction to be executed in memory. It's basically a register. So here we see it's currently at address 0 because we haven't started the CPU yet. So this will then send the data to the MAR, which is the memory address register, in order to fetch data from that memory address. So after that's happened, the program counter needs to be incremented by 1 in order to go to the next memory, or to point to the next memory address that an instruction will be in. So in order to do that, the output from the program counter register itself is sent through an incrementer, which increases it by 1, and then is clocked back in to the register to point to the next address. So we can demonstrate here, yeah, that if I clock the register, every time I clock it, it increases by binary 1. We'll just have a quick look at the incrementer circuit. It just takes the address and uses a series of 4 adders, which we'll see later during the addition circuit, and adds logical a constant 1 to it every time. So this is the result. If I input the next one, it will go to the next, and we can see here that the result is correct. So that's the program counter. Oh, the program counter also needs to be able to branch to any address in memory. So during a branch condition. So in order to do that, the enable branch is set and the program counter is clocked, and then the program counter will take on the value of whichever memory address has been set in the branch. It's worth noting that throughout the CPU, in order for data to travel on the bus, we'll go back to the main bus, in order for data to travel onto the bus, it has to be 16-bit because that is the largest data that has to travel along the bus, and components in Logisim connected to each other have to have the same input and output width, even if the tri-state gates aren't enabled, so they're not directly interfering with each other, they all have to be 16-bit. So because we have 32 memory addresses, the memory address being transferred will be 5-bit, but we use filler zeros, as demonstrated here, and bit splitters to add extra bits that will just be 0 onto the memory address in order for it to travel onto the bus. And that's the same when it's being input here as a branch. This method is used throughout the CPU, and it's pretty simple, but if anyone has any issues, then they can leave a comment and I'll try and explain it in more detail. So the memory address register takes the address from the program counter and uses it along with the read and write from memory in order to get the instruction from memory. It's just a simple register. These are all D flip-flops, so it will be, because the register is 5-bit, it will contain 5 D flip-flops here. 1, 2, 3, 4, 5, and an allow write so that data isn't overwritten when it's not meant to be. The memory unit itself contains 32 addresses of 16-bit. It takes an address input, a data input, a write enable input, and a read input, along with some other manual inputs here that I set for testing. So an address will come in from the MAR, and it will be decoded using this 5 to 32-bit decoder, which looks like this. It's just a simple decoder. You use a load of AND gates, all connected to each individual bit and the negation of that bit in order to get a unique output for every individual bit. So if I increase this, it'll go to the next, and then they'll keep going up and such, as we can see there. So back to the memory addressing. Once this happens, these individual decoded bits all point to an individual 16-bit memory line. So we have 32 of those subcircuits inside this component. So we'll look at those. The 16-bit memory line holds 16 individual D flip-flops, as we can see here, which each hold 1 bit of data. So we need 16 of them in order to store our 16-bit memory address. If the write enable and the enable from the decoder are active, then the memory can be written to. So we can write 1 into this, and it should output as 1 here, or 2 even here. And these are all controlled by the control unit. Memory address. They're combined. The 16 bits are combined at the end and used with a multiplexer with the address and the read enable to select from one of the 32 addresses, and this is then output onto the system bus. Back to the main circuit, so that's where the output will be, and if emem enable memory is enabled, then that data will flow onto the bus, and during the fetch phase, this will be clocked into the instruction register. The instruction register is just a 16-bit register which holds the instruction and partially decodes it, but mostly sends it to the control unit for decoding. But some of the operands are decoded here with bit splitters if they're register values and sent into the registers file, or if they're literal values, they need to be used. They are enabled onto the bus and used inside the ALU if necessary. The registers file contains 4 8-bit registers. These are just general purpose registers that are used in calculations. They're very similar to the memory address register with D flip-flops. There'll be 8 in this case though because the data is 8-bit in. Yeah, these are all just D flip-flop circuits here. And back to the registers are all contained in a single file with data in from the bus, the source address, register address, the destination register address, and write destination, write source, and demultiplexers are used to select which of the memory addresses, which of the register addresses are being used or written to or read from. Don't worry about these error values for now because Logisim doesn't know the values of these registers since we have not put a value in yet. They do not default to 0 like the pre-built Logisim components do. And data from these registers can be read to either bus A or bus B, which are both inputs into the ALU. Here is some logic to write the source register to A, write the destination register to A, or write the destination register to B and the source register to B. It's a bit messy, but this is a necessary feature in order to implement some of the instructions such as subtraction, where operands will be different ways around. So you would subtract the source from the destination and put it in the destination. So it's necessary to have this in this way. Back to the main. The ALU controls or performs all of the operations in the CPU itself. So if we go into the ALU circuit, we have a look at it. It contains an adder circuit, a subtractor circuit, a multiplication circuit, and or not an XOR gate. The ALU takes 2 16-bit inputs, but only performs the operations on 2 8-bit words because of the 16-bit numbers necessary to travel along the bus. But the first 8 bits, which are zeros, will be split off, and the operations will actually be carried out on 2 8 bits. So the adder will add 2 8 bits, the subtractor will add 2 8 bits, subtract 2 8 bits. And based on the opcode input, which is here, the opcode is normally 4 bits, but in this case, logical and arithmetic operations only require the use of 3 of those bits, and the rest of them are used to encode branching, instructions, and other things like trap to read to the user interface. So if we look at each of the individual circuits, the adder circuit adds 2 8-bit numbers, as we said before, with a carry-in input, and uses full adders like in the incremental circuit. Full adder is made like this. So this is the full adder circuit. It just adds two individual bits and generates a sum and a carryout. Again, these are error values at the moment because the values are unknown because the CPU hasn't run yet. And back to the adder circuit, 8 full adders are used, with the carry output being used as the carry in for the next adder in order to account for the carry bits. This is called a ripple carry adder, and it will be the result will be 8-bit as well. And there may be a carry out, and that is calculated here by using the last carry out of the last full adder. The subtractor circuit, similar to the adder circuit in the sense that borrows are used as input into the next, or carry out are used as the input into the next circuit, subtractor circuit. So these are full subtractor circuits, and there are again 8 of them with a carry out a similar way to the adder, apart from they subtract obviously. The multiplication is a little bit more tricky. Multiplication is calculated using addition of partial products using the Borg-Woolley algorithm. You do this by taking the AND of the individual bits and using full adders and half adders to add the partial products in order to create the result at the end. Carry is calculated if the input is over 8 bits, and the logical operations are just simply input into Logisim's gates. An XOR circuit could have been created. Technically, XOR is not an elementary gate, but I felt like it was unnecessary to add this for neatness. So, in order to select one of these operations, a multiplexer is used with opcode inputs, which are again controlled by the control unit, and these will select the result. So if the input is 1, if the opcode input is 1, then the first addition operation will be selected and an output as the result. Carry and zero flags are also calculated in order to perform branching instructions. These are stored in a condition control register, and they are input into the control unit so that it can tell if a branch condition is met or not. These are selected using a multiplexer again, but because logical operations don't generate a carry bit, it only applies for addition, subtraction, and multiplication. So this multiplexer has 0 inputs for other things that are not those operations. Also, the move operation goes through the ALU because of the registers not being directly connected to the bus. So this piece of logic here just says that do not override the carry or 0 flag if the operation is just a move one. So this is not updated if a move operation, because that could corrupt some of the results for branching. So that's the ALU. Something to note is this register X here, which is just a simple register. It's an 8-bit register, so that you can store intermediate values after an operation has been performed, because generally if a literal value is being used or a value in a memory address is being used, it will travel along the bus and into the ALU through these multiplexers. And so since 2 pieces of data can't be on the bus at the same time, you have to wait another clock cycle. So the calculation is performed and then is clocked into this intermediate register. And once the data has left the bus, the intermediate register is then put onto the bus and data is saved wherever it was meant to be saved. So that's the individual components. And the control unit. So the control unit controls the whole circuit. So it's all of the tri-state gates. It has an instruction input, and it also has the carry and zero flag input for conditional branching. It contains a sequencer, which is made from JK flip-flops, which sets the timing signals for the circuit. It has a clock, and if I tick the clock, it should go to the next time signal. Here it is. So this is time t0, this is time t1, up to time t7. This is all we need for this implementation, but if you needed more timing signals, more JK flip-flops could be added in. The control unit uses an RS flip-flop to change between fetch and execute phases. At the moment, it's in the fetch phase, designated by this Y here. So when the timing signals are combined with whichever phase, so here, to perform the first part of the fetch phase, T0 will be enabled, and so will the fetch phase, and this will lead to the fetch T0 output being used in order to set the control gates that are necessary. So if we have a look along here, fetch T0 is input into this OR gate, and this clock mar will be output into the main circuit and will clock the mar. And these gates will be set at the appropriate times, as you can see by these tunnel labels. And there is one OR gate for every tri-state gate or selector bit in the circuit. So during the fetch phase, the program counter contents is sent to the memory address register. The data is then read from that address and input into the instruction register, and then the fetch phase resets and the execute phase is initialized. So if I clock, this is the execute phase now being initialized. With the fetch phase, at the end of the fetch phase, the set input is input into the RS flip-flop, which then sets the output to true, which enables the execute phase. The execute phase then enables these gates to be true. So this is simple decoding logic, like in the big decoder that was used. It decodes the addressing mode and the opcode being used. But before we get into this, we should probably look at the architecture of the instruction to see how instructions are made up. So the instructions are 16 bits in length, as depicted here. So the first 4 bits here are the opcode. Now the opcode is whichever instruction is being executed. So you can see a table of opcodes here and which operation they perform. So 0000 will be the move operation, and it moves the contents of one data register to another, or the contents of memory to a register, or immediate value to a register, whatever the addressing mode is. Now that brings us on to the addressing mode, which are the next 2 bits. Now these aren't exactly addressing modes because having a register to register, a memory to register, and a register to memory are all absolute addressing, but they need to be encoded with different numbers because different gates need to be set, so I've named them addressing mode here. There's also an immediate to register value, which is where you'd move a literal value, so the number 4, to a register of your choice. And to decide which register you want to use, operand 1 is used because every every instruction has to contain a register, which is why it's a 1.5 address machine. And so since we have 4 registers, only 2 bits are needed to encode operand 1. Operand 2 can either be a register, which in case would be these 2 bits, if the addressing mode was 0, 0, where we'd have a register and another register, or it could be a literal value, which can be up to all of the 8 bits if the addressing mode was 0, 1, or it could be a 5-bit memory address if the addressing mode was 1, 0 or 1, 1. So that's basically the makeup of the instruction. Now back to the control unit. The 16 bits are split using a bit splitter, and the first 4 opcode bits and the next 2 addressing mode bits are used in the decoding for each of the operations. So we have the move decoding here, but we also have the addressing mode for each move. So we have move 0, 0, addressing mode, move 0, 1, addressing mode, moves 1, 0, and 1, 1. And we have this for all of the operations that can be implemented. Apart from the branch instructions like BQ, BN, E, BHI, where addressing mode does not matter, but we have the conditions sent from the ALU instead. So our trap also has 2 modes, but we'll discuss that later. So when the execute phase is initialized, the AND gate will be true of whichever instruction is come in. And so in this case, it's move 0, 0 because we haven't actually got an instruction, it's just zeros. So we'll go down, and at time t0, the move 0, 0, t0 instruction part will be executed, which will set some of the timing signals, like clock X here, and we'll set the appropriate ones in order to implement that part of the instruction. And then at T1, the next part will be implemented, such as there's a one here for writing to the destination register. And at the same time, we can look around here, the RS flip-flop will be reset and will return back to the fetch phase to get the next instruction. And at the same time, the sequencer will be reset back to T0. And this is important so that the fetch phase can start on T0 and not be on T3 or whichever timing signal it was. We'll go back to the main CPU circuit and actually load a program into memory. The memory addresses, the contents of memory can be displayed here. And there's also a screen output to read to convert binary to decimal, so that it's just easier for people to see results of calculations. In order to populate memory, the Logisim ROM component was used, which allows users to save programs that they've written and load them up at any time they wish. You could enter manually using pins like these if they were input pins into the memory, but this would take a long time, and every time you open Logisim, you'd have to write the program in again. So it's just easier to do it like this. So we populate memory, we disable the clock in the control unit so that it can't execute anything at the moment because the control has been stopped, and because all Logisim clocks are linked, so that would continue ticking and would break the circuit. So we load that and we set text to be enabled. Now we can see that the program I have selected has been loaded into memory. I believe this calculates 5 factorial, which is 5 times 4 times 3 times 2 times 1. And here we can see this is the program. So from our architecture, we know that the first 4 bits are the opcode. So this is a move operation with addressing mode 0, 1, which means it's moving a literal value from register 0. Well, it's moving the literal value 5 here to register 0. So if we go through this step by step, we should see that initially we want to fetch the instruction from memory. So if we tick once, the instruction has been fetched from memory, and we can see that the whole instruction is inside the instruction register and is going into the control unit ready for decoding. The PC should still point to the same address. Yes, it does. It points to 0. You can see the instructions are currently on the bus and it's being read from memory using the enable memory bit down here and clocked into the instruction register. So on the next clock pulse, the PC is clocked, which will now mean it will point to the next memory address, which should be 2 when it's falling edge, so it'll be in the next cycle. And once that happens, the execute phase is now initialized. If we go into the control unit and have a quick look, the execute phase is now initialized. The timing has been reset to time 0. The move 0, 1 operation should be enabled, which it is here, we can see. And if we go down to see which timing signals have been set, move 0, 1 can be done in 1 clock pulse because you're just simply moving an intermediate value or an immediate value from the instruction register straight into the register file, which means that there are no conflicts on the bus. However, if you reset at time t0, the fetch phase will instantly be executed and this will cause conflicts on the bus. So we need an extra timing signal t1 just to settle things down to make sure that there are no conflicts on the bus. So if we go back, we should see that yes, 5 has been clocked into register R0 as we expected. And now that we've clocked that, the timing should reset and we are now back on the fetch T0. So we fetch the next instruction from memory, which is another move operation, and it's moving the literal 5 into register R1. So again, we clock, we fetch the instruction from memory, from the next memory address, and we should see down here that it gets clocked into R1 as we expect. And so the operation involves subtracting the literal 1 from memory, from the register address 0. So again, it's the same process. Tick to clock the value into the instruction register, then into the execute phase. The instruction register should be enabled that allows the literal 1 into the ALU using this multiplexer. I should have explained these multiplexers earlier, that you can read literal values or values from memory from the bus, from the main bus, into the ALU operand B or A, or you could read the register values onto B or A. So you use multiplexer to decide if you're reading from the register file or from the main system bus. So in this case, we're reading from the register file here. So we're reading the source to A, and that's in the 0 input to the multiplexer, so A is not enabled, and that will flow into the ALU. And the literal 1 from the instruction register should be on the bus, yes, and it's flowing into 1 here in the multiplexer, so B needs to be enabled. These are all set by the control unit here, and we should be able to see that the addition the subtraction even has taken place. So we've got 5 here, we're subtracting 1 from it, and the result is 4. Because of the opcode, the subtraction operation is chosen. And if we go back, we should see that it's clocked into the intermediate register X because we have something on the bus already, so it cannot go straight back into the register R0. So if we take again, we should enable, oh yeah, so the value has been enabled onto the bus and has been written into R0 at the same time as the reset has happened here. So it was too quick to see, but it has happened. We can see that the result has happened. So onto the next address. I think we've already fetched it. Yes, it's a multiply register to register this time, not the 0, 0 here. R0 and R1. So we're timesing R0 by R1. And this is to be expected because we're working out factorial. So we have working out the 5 times the 4. So we'll just calculate that. And there we have the result, which should be correct. And then once we have that, we're using the branch if not equal instruction, which means we have to look at the 0 flag, and if the operation has enabled the 0 flag in R, if R1 contains the 0 flag, then the condition would not be met, and we would continue here where we would trap the result being output because we would have finished the program. But actually, the condition has not been met. R0 does not contain 0 currently. So in this case, we branch to address 1, 1, which is here, where we go back and we subtract again and repeat the process. So we should see here, if we clock the branch instruction in, we can see that it's been met. And we've gone back to an instruction here, and it should subtract 1 from R0, as we can see. So if I let that run, we should eventually get to R0 being 0, which we have. The 0 flag is enabled, and this means that the condition was not met, and so the trap function was implemented, which converts the binary value here into a decimal value here using this subcircuit, which we will not get into today. But once this has happened, just a filler stop program is used, or a stop instruction is used, which just stops the control unit's clock from pulsing. So we know that the instruction has been executed correctly. 5 factorial is in fact 120. And yes, so that's basically the CPU. If you have any questions, feel free to leave them in the comments. And thanks for watching. Bye guys.